careful, guess.
No, we can't.
Don't make a mess.
Yeah.
This physics class is brought to you by our friends at Coke Zero. Sponsorship deal. All right. Can you write that down? Conservation of energy. You got that? Yeah. You got that?
No.
What does the word conservation mean?
Conversation? No,
Conservation.
wait a moment.
No dictionary. What does conservation mean?
Reserve.
Reserved, yeah.
Easy, but not all.
No, I like reserved, or another word, constant. So, we'll talk about that more in a little bit. But why do we care about energy? So, firstly, what is energy? So does anybody know? I mean, we all kind of understand this word called energy. We can say this has a lot of energy and a little energy, but yeah?
Is work done per unit time?
No, that's power.
The ability or capacity to do work.
That's it. It's an ability to do work. So, if something has energy, or is energy, then what do we mean? We say in physics that something has or is energy if it has the ability to do work. So if a person can do some work by applying a force over a distance, then we say that person has energy. So this is a standard physics definition here of energy. Yeah. Now, it's also measured in joules. No work means no energy. No energy means no work. So they're nearly the same thing. But there's a small difference. The work done is always less than or equal to the energy available, which makes sense. You can't do more work than the energy you have inside of you. You know? If you have 1,000,000 joules of energy inside of you, that means you can only do up to 1,000,000 joules of work. Right? However, most problems we look at, all the energy gets used up into work. So a lot of the time, work and energy for us will be the same number. You know? We kind of imagine all of the energy went into all of the work. Yeah? Okay, you can make a little note of anything here that you feel is important. The most important thing, though, is the definition. Yeah? Yeah, you got that? You got that?
Yeah.
Continue?
Yeah.
Which I can do up to now. I can do up to.
Say again?
The.
Oh, yeah, that's right. I should say up to, shouldn't I? There's an extra 2 in there. Okay. There are many types of energy, many forms of energy. So we'll run through the list of some of the big ones, okay? So the first type of energy is electrical energy. This is a very important type, isn't it? So all I need you to write down is the list. So number 1, electrical energy. Yeah?
Yeah.
Yep, okay. Next, magnetic energy. You got that? Magnetic energy. Yeah, okay. Next one, chemical energy.
Yeah.
Okay, next form of energy. This is energy from light, radiant energy.
Sorry?
Energy from light, radiant
It's
energy.
not sun.
Yeah, yeah.
It's a sun energy.
But it's not just from the sun, it's from any
From
light.
Oh, okay.
Yeah, yeah. Radiant energy.
Mm-hmm.
Yeah,
Yeah.
continue. The next type we have is nuclear energy.
Nuclear energy
Yeah, you know this one, don't you?
is for factor.
For what?
Factor.
Fracture?
Factor.
Oh,
Factory.
Factory?
Yeah.
Well, it could be for anything, really. Yeah, it could be for anything. Yeah? Okay. Next one. So you did this one in chemistry. Ionization.
Yeah.
You've done ionization, haven't you? Haven't you?
What's it? Is
Ionization energy? No? Have you done ionization in chemistry?
no idea about that.
Yeah, well, okay. Have you heard of it before? That's enough. Right, next. Elastic energy. Yeah? Yeah? Got that? Got some biscuits there, huh? Right. Gravitational energy. Gravitational energy. Next one. We'll get, yeah, heat. We'll get to heat energy.
Heat energy.
Yeah. Okay. Next.
Is
Mechanical energy.
mechanical.
Yeah.
How to spell?
Like in a clock. So I'm on the top there, see?
So there's gravitational force and gravitational energy.
Yeah.
Mechanical.
Yeah. Like in a clock.
Oh yeah.
Yeah?
Swiss clock.
Swiss clock even, yes. Right, continue. Wave energy. Yeah. Oh, there's many type. Yeah. Hydrogen cells are one type. Yeah.
I think.
Wave energy. Yeah. Kinetic energy. This is the energy due to motion, movement.
Isn't that undone?
Potential energy.
No, it's a little different to mechanical. And then the last one is, yes, potential energy. So this is the energy something has due to its position.
Are we going to learn all those things?
No, we're just going to look at kinetic and potential. Yeah?
Radiant and solar, the same thing.
Pretty much, yeah. Yeah. Solar would just refer to energy from the sun. Yeah, it's a type, it goes into the category of radiant. Okay, can I continue? Yeah. So, this is the most important rule in physics. It's called the conservation of energy. And it's the most important, it is the most important rule in physics. It says that energy can be neither created nor be destroyed, but it transforms from one form to another. So that means, let's take the example I take is with the projector. So, what type of energy is coming out of the projector? Well, there's three types really. There's light, heat, and a little sound. Yeah? Yeah. So you got three types. Okay. Where did this energy come from? It didn't just come from nowhere. It came from the electricity. The energy coming out of the projector will equal the energy that went into the projector. So the energy wasn't created, it was just transformed from electrical into light, heat, and sound. Where did the electrical energy come from? It wasn't created. Where did it come from? Maybe solar, maybe nuclear, maybe what else? Not mechanical. Yeah, but where did the generator get its energy from? Maybe, or maybe just burning fossil fuels. So that would be chemical. Yeah, chemical, right? But the energy in the oil, where did that come from? Yeah, but where did that energy come from?
Dinosaurs.
Yep. And where did the dinosaurs get their energy from?
Plants.
Plants. And where did plants get their energy from? Sun. You see? You can keep tracing it back and so forth. Okay? So
But like the sun is like the major source.
say again?
The sun is the major source.
Ultimately, for us, all energy, you can trace it back to the sun. So, for example, I'm getting energy because I'm drinking coffee. The coffee beans that have the energy in them that were grown in the ground, they got their energy from the sun, and that energy was stored in the coffee bean, and now it's being released as I drink it. You know, so one way or another, all the energy you can trace it back.
To be somewhat like the sun got its own.
Yeah, we have to start thinking about this. So, the energy in like the sun and other stars would have gotten their energy from the Big Bang. Yeah. So, how far back you want to go starts becoming a matter of personal taste. You know, what?
No, nothing.
Yeah.
The Big Bang Theory.
Yeah, well, it's true. It's true. All the energy in the sun came from the Big Bang.
Where did the Big Bang come?
Well, see, this is the thing now.
Big Bang.
Think about it.
Like,
12 billion years ago. 12 billion. 13 billion years ago. Okay, so this is the most important rule in physics. And the reason it's the most important rule in physics is because there is no exception to this rule. There's no exception. So when you take, we did Newton's second law, F equals ma. Now believe it or not, that law is true 99.999% of the time. There are some examples of when this law is not true. Okay? What are other laws we did? Newton's law was a big one. Conservation of energy is the only law that doesn't have an exception. You know, which is what makes it so important. So, next now is the kinetic energy. If an object is moving, then it has a kinetic energy. This energy is from some work being done on the object. That is, kinetic energy gives work done to give that object. So look, you don't need to write this down just yet. What I want you to write down is the short little proof here for calculating kinetic energy. I'll give you the diagram here. This is what's happening. This mass here is moving with a velocity v.
Yeah.
Now, we say that this has kinetic energy because it can do work. Like, for example, if I need to break something open, well, when this crashes into it, it will do that job. Right? It has energy in it that we call it kinetic energy. But where did that energy come from? Mass, no, not this one. This energy came because probably what happened was this was at rest and then somebody pushed it. So the kinetic energy that this has is equal to whatever work this person did to give it this situation, to put it in this situation. Okay? So we can work out a formula for kinetic energy. The kinetic energy will equal the work done to get the mass in this situation. And the work done is the force times the distance. But what did Newton say force is equal to?
That's
MAS.
MAS.
Well, a force is MA, so we get MAS here, yeah? Now, U equals 0. V we don't know. A we don't know. T we don't know. S we don't know. U equals 0 is the only thing we do know. If I use the formula V squared equals U squared plus 2AS, the U squared is 0. And so what would AS equal? V squared over 2. Now I'm going to sub that in there. So now I get KE equals V squared over 2 times M. Remember I'm replacing the AS. Or, as it's more commonly written, a half mv squared. This is the proof for the formula for kinetic energy. This gives you the amount of kinetic energy the object has of mass m traveling with speed v. Yeah? So the proof is short. You don't need the proof for the exam, but it's a nice little proof. I think you should write this down. This is the kinetic energy formula. Okay, you got that?
Yeah.
Okay. You got that? Yeah, continue? Okay. Okay. You got that?
Yeah.
Yeah. Now, the next one we'll do is the potential energy. So, let's imagine there's a mass up here at a height of h. This has potential energy because it's about ready to fall. When it falls, it hits the ground and it can do some work in the process. So, the potential energy it has is equal to the work done. What work was done to it, though? Yeah, somebody must have lifted it up to this position. Yeah? So again, work is force times distance. In this case, the distance is h. But what force was applied to it to get it up into this position? How much force? Well, it had to be equal to the weight. Right? Yeah? Yeah? And what's the formula for weight? And this is the formula for potential energy, mgh. Okay, you got that? Yeah? Okay. So, whoops. Now, we've had a look at kinetic and potential, so so now talk about potential. So potential is actually a little bit different to kinetic. Kinetic energy, what's the formula for it? It's a half mv squared. Could that be negative? No, why not? Yeah, it's v squared. Yeah. Could it be 0 though? Yeah, what would be happening if it's at 0? It's not moving. Yeah. Now potential energy is a little bit different, because for potential energy you're allowed to have positive, negative and 0 as an answer. And in fact, that's kind of common in physics, the 3 situations. So we need to look at what each situation means. So when the potential energy is positive, like I'll draw a picture here, potential energy is positive, it just means that the mass is above the ground. It has energy stored inside of it, like this here. So, we say the object has potential energy. Fairly obvious, okay? Now, what if the potential energy is 0? What might that mean? It's on the ground, isn't it? So, if the potential energy is 0, the mass is on the ground. Now, how do we describe that? In physics, when this happens, we actually say that the object is now free. In the first picture, it's not really right to say the object is free, is it? Because it's only going to move one way. What way is that? Who said up? Who said up? How many objects fall upwards? In the first picture, it's not free to move any direction. It'll move which direction? Down. However, now that it's on the ground, it can move left or right. So its movement is now free. Okay? The last one, well, actually, you might want to write this down. Then we say the object is, quote, free. And that is a term in physics. If you say an object is free, we mean that potential energy has no, potential energy is 0. Now, you've actually seen this a little bit in chemistry already, okay? If you want to free an electron, you have to give it energy. What's that called? Ionization. So, free means that you want to get it out and not to be bound to the atom anymore, to the nucleus anymore. This one here, it's kind of bound to the ground. You know, you can't just, you'd have to do something to get it away. Next and last one is, what do we think it means to say the potential energy is a negative? Where do we think it is? What's going on? What is it? Yeah, so in my picture here, what should I draw? Yeah, it's basically going to be underground level here in this picture. Okay? And here we say that it is trapped. Trapped. Because if you want to free it, where would you have to move it to for it to be free? You'd have to move it to the ground. And the only way to move it would be to apply a force. And you would have to apply the force over a distance. Therefore, you would have to do work. So you would have to do work to free it. It's trapped and requires energy to be freed. This is exactly the situation with the electron in the orbit. Okay? The electron is trapped in an orbit. You need to give it energy to be free. and to remove it from its orbit. This is called ionization. Yeah? How could you give the electron energy to be free? What form of energy? Light would do it, yeah. You could shine light on the nucleus to free it. Anything else you could do? Charge it? How? What form of energy?
The fall.
Well, I don't know. I think if you heat it, right? If you heat a gas, do you not ionize it? Do you not free the electrons? You do, yeah? So heat energy can be given to the trapped electron to free it, ionizing it. I'm only giving you this example because I taught you did this in chemistry. Are you sure? Kind of. Okay. Anyways, you get the idea? I'm trying to think of another example. Yeah, so like, I mean, if you just have two things stuck together, you could say the potential energy is negative because you would have to do work, give it energy to free it.
So that's
Yeah? Yeah. That would have even more negative potential energy than just being underground. Okay? So, you will need to know this. It's useful to know that the potential energy is negative when it's trapped. Okay? So, I think it's good. It's nice if you can draw the picture too, but you should write this down as well.
if you use that, it's free.
No, not
Right.
free.
Right.
Because you would have to. Well, what are you talking about? Which part of it?
I mean, it's, if energy is free,
Yeah?
it's if you use this first and this first, as energy is free.
No. The helmet, that's free.
Yeah.
Its potential energy is 0 because it's on the table.
Okay.
You could easily move it left or right.
Uh-huh.
Now, if you put that helmet on the ground, we say it's trapped. You would have to do work to get it back to the table.
Oh, yeah.
Yeah, but if you lift the helmet up, it has positive potential energy because it's going to do work. It's going to start to fall and hit the table.
Oh.
Yeah.
So if you just stay here,
It's free.
It's free.
Yeah.
Okay, I
Yeah.
understand that.
Yeah. Which I know seems a little strange, but that's what we mean when we say free. Okay, is that okay? Can I continue? Yeah. So, next now, the conservation of energy implies that the kinetic and the potential must be constant. In other words, remember earlier we said energy can't be created or destroyed?
Yes.
What that means as a formula is the energy at the start, E1, equals the energy at the end, E2. Which means the kinetic at the start plus the potential at the start should equal the kinetic at the end plus the potential at the end. Okay, can you write that down? You got that?
Please enter.
Okay.
Okay.
Yeah. Got that, folks? Yeah. Okay. I'll skip that example. It's a little too. Yeah, we'll do this example. No, actually, I'll do this one here. Sorry. Okay. All right. So I'll just give you a diagram example here. So let's say we have something like a roller coaster, something like that, and here is the roller coaster at the top here, and then here it is at the ground here, and we'll say it's a height, I don't know, 50 meters, something like that, and it's at rest here. and then it'll fall down, and then it'll be moving here with a speed v. And my question is, how fast will it be moving? So this is a good example of how useful conservation of energy is. Let's look at the energy at the beginning. So, firstly, E1, what's the kinetic energy? 0. Why? Is at rest. And what's the potential energy? M, which we don't know, G, which we do know, and H, which we do know, is 50. So the energy at the beginning is 50 mg. Right, let's look at the energy at the end, on the ground. What's the kinetic energy? No, kinetic energy. A half mv squared. Plus, what's the potential energy? 0. So what is the total energy at the end? A half mv squared. Now, the conservation of energy says the energy at the start equals the energy at the end. Therefore, 50 mg should equal a half mv squared. What can I cancel on both sides? M. I'll multiply by 2, so what's 2 times 50? 100g, which is 981. Yes? And that's equal to what? V squared. So what does V equal? Square root 981. And that's the answer. So this is quite nice because do you know the mass? No. Do you know the shape of the roller coaster? No. No. But yet we can still know the speed of the trolley, the carriage, at the ground level. Which I think is quite interesting. Because you might think, oh well, maybe the shape here affects it, you know? If it was steeper, maybe it'll be going faster. But actually no, it doesn't really affect it according to this. Okay, write that example down. Yeah? No. Hey. Oh, yeah. Ah, the paper.
We all do paper, don't we?
Sorry, everybody.
Okay, do you have that written down? No? Do you have that? Are we just waiting for you, Bello? Oh, Bello, come on.
It's not lose energy like heat or something.
Yeah, in real life it does. We'll have to talk about that later. This is what's called efficiency. You know this word? We'll talk about that in a different lesson. Okay, continue. So, let me give you one to try, and then I'll give you the answer. A 200-gram bullet is fired horizontally from a height of 10 at a speed of 100. How fast is it going when it hits the ground? I'll just give you a quick sketch, and then I'll go back to it. So what you have is you have a bullet here, and it's fired at a height of, what did I say? 10. And it'll come along, and then it'll hit the ground eventually. And my question is, what's the V here? All right. Okay, I'll give you a minute to try this. Let's see if you can get it. Is that your phone? Okay. Did you take the sound out, maybe? Okay, you got that? Yes? No? You have it? Okay, I think that's plenty of time. It's not that big of a question. Let's have a look. So, what type of energy does it have at the beginning? It has both. Yeah, it has potential energy, which is mgh, and it has kinetic energy, a half mv squared. At the end, what type of energy does it have? Just kinetic, which is a half mv squared, and that should equal that. Fine, okay, so by solving, what did you get for V? 17.2? Thank you. It's okay? Yeah? Yeah. Yeah. Okay. Right. Not too difficult. Let's see. How many questions do we have for this lesson? Let's have a look, see. Oh, come on. Come on. Let's see. Server. Okay. Generator tool. And physics workbook. Let's see. Slow internet. I still have to get you a USB key, son, don't I? So you can give me the video.
Teacher, your USB-C is...
I left it at home.
Huh?
I left my USB key at home.
Oh. So you will get tomorrow?
I'll bring it tomorrow, yeah.
Because I already sent to your email, you can try to find it. If you get, if you cannot, you bring to the USB.
Oh, I don't mind waiting. You can continue uploading it.
Because I already sent to your email today.
Oh, did you? My email broke yesterday. My account's not working.
Okay, sorry about that.
Yeah, no, this is the stupid computer. Stupid. Right, what have we got? Okay, there's only 8 questions, and as you can see, they're not, like, look at this one, it's not that long to do, you know? So, oh yeah, okay, I'll let you try these for a few minutes, and then we'll start the next topic. What is the next topic, actually? Power and efficiency, which is what you were just asking me about.